We present a gyroscope-guided unsupervised learning approach for optical flow estimation. The deep learning-based approach learns the regression of each pixel directly through convolutional neural networks. They can be divided into supervised and unsupervised methods. The former method is mainly trained on synthetic data due to the lack of ground truth labels. Moreover, it is more difficult to obtain labels in challenging environments, such as darkness, fog and rain. Unsupervised methods can be trained on video sequences. However, they are error-prone in challenging scenarios because the basic assumptions of optical flow are broken. Here is an example in a foggy environment. The first column shows two input frames. The second column is the prediction of raft, which is the state-of-art supervised method. It suffers from domain adaptation problem. The last column is the output of U-flow, which is an unsupervised method where the optical flow in the sky is incorrect. In order to improve the performance of optical flow in challenging scenes, we introduce the gyroscope. Gyroscopes record the three-axis angular velocities reflecting the camera rotations. Based on the camera rotation, we can compute an array of homographa and subsequently generate an offset flow named the gyro field. With the help of gyro field, two consecutive frames can be aligned. Thanks to the image content independent property of the gyroscope, the background areas are well aligned even under weakly textured conditions. On the other hand, the moving objects are under-aligned because the gyro field is confined to camera motion. From above observations, we notice that the gyro field and optical flow can be complementary. Our motivation is to improve the background motion of optical flow while guiding the network to focus on foreground motion. So we propose a new framework, the GyroFlow. The last column shows our result, handling both the background and foreground optical flow in the challenge scene. Our network is built upon upflow that inputs two frames and the corresponding gyro field. Furthermore, it consists of two stages. The pyramid encoding stage is to extract multi-scale feature pairs. And the pyramid decoding stage is to estimate optical flow in a coarse-to-fine manner, which includes the self-guided fusion module. Here is the detailed structure of SGF. Given the input features, the corresponding gyro field and optical flow from the previous layer, we first implicitly fuse the gyro field and optical flow in the fusion block. Then we compute a weight map in map block to explicitly fuse the gyro field and the output of fusion block to produce the final result. To validate our method, a new dataset named GOF is proposed, which contains 4 categories with synchronized gyro readings, including regular, low light, foggy and rainy scenes. Some ground truth labels are shown below. In GOF dataset, we collected 8,000 pairs of images as the train set, and each category contains 2,000 pairs respectively. For the test set, there are 400 pairs of images with ground truth labels, and each category contains 100 pairs respectively. Here shows our experiments. We compare our method with existing supervised and unsupervised methods on GOF benchmark. And our method outperforms all the previous methods. In particular, we achieve EPE error of 0.74 on the regular category, and 0.72 on average, which outperform the previous state-of-the-art methods by 16.6% and 26.5%, respectively. Here are some qualitative results on GOF benchmark. For each example, the first row shows the visualization of the optical flow and the second row shows the error map. Compared with the results of AR flow and U-flow, our prediction flow is more accurate and cleaner. Here is our ablation study on the GOF benchmark. In the first table, we find that the proposed gyro field and self-guided fusion can individually improve the performance. While combining them together, the performance can be further improved. In the second table, we find that a noticeable improvement can be achieved after inserting our SGF module into a different backbone. To summarize, we propose the first DNN-based framework that fuses gyroscope data into optical flow learning. We propose a self-guided fusion module to effectively realize the fusion of gyroscope and optical flow. We propose a GOF dataset for the evaluation. Experiments show that our method outperforms existing methods. Thank you very much.